All right, welcome to your very own deep dive. We're going deep into data structures, especially since you're digging into that Chinese textbook, Changjie.
Oh yeah, that's data structures in stupid simple terms for anyone who doesn't read Chinese.
I love that title. It's so catchy.
It really sets the tone for the book, too. It's written by Chengzhi, published by Tsinghua University Press, and they weren't kidding about that stupid simple part. Even the cover's got this cartoon style to it, you know?
Yeah, definitely not your typical textbook vibe. You mentioned you were particularly interested in chapter 2, right? The one on algorithm efficiency.
That's the one.
Perfect. That's where we'll focus then. It tackles some pretty big questions, like how come one way of solving a problem can be so much faster than another way, even if they get the same answer? And how do you even measure that speed when it comes to computers?
Those are great questions, and the book jumps right in, laying out what an algorithm even is, a set of instructions for solving a problem.
Sounds pretty basic, right?
It is. But what Chengji emphasizes is that it's the method that matters, not just the answer you end up with.
Oh, that's interesting. So, like, if I asked you to add up all the numbers from 1 to 100, most people would just start adding 1 plus 2 plus 3 and so on, right?
Yeah, probably.
But the book tells this story about young Gauss. I mean, this kid was brilliant. He figured out a much faster way to do it.
Oh, yeah, I remember that story. He was definitely not messing around with that long addition.
No way. Instead of just adding one by one, Gauss paired the numbers up, so 1 plus 100, 2 plus 99, and so on. Each pair adds up to 101.
And you have 50 of those pairs, so boom, the answer is 50-50. Way faster.
Exactly. Same problem, same answer, but a completely different way of getting there. And that's where algorithm efficiency comes in.
You got it. And the book really stresses how important this gets as the problem size grows. Like, imagine searching for a contact in your phone. If they had to go through every single contact one by one, that'd take forever, especially if you have a ton of contacts.
Ugh, that would be a nightmare. I'm glad my phone doesn't do that. But, okay, how do we actually measure and compare how efficient different algorithms are?
That's where big O notation comes. And the book describes it as the shorthand to see how an algorithm performs as things scale up.
So is it like the bigger the O, the worse the algorithm is?
Not quite. It's more about how much the time or resources an algorithm needs increases as the problem gets bigger. A simple one is ON. That means the time grows proportionally, like our friend adding up the numbers one by one.
Okay, that makes sense. What about something like ON2, though?
That one means things get much worse, much faster. As on, the amount of stuff you're working with increases. The time doesn't just double or triple, it squares.
So ON2 is basically like saying, this algorithm is going to choke if you give it too much to handle.
Pretty much. And to show this visually, the book uses a graph. It compares different types of algorithms, and it's really clear that some get terrible as the data size grows.
So we've got ON, ON2. Are there others? What about algorithms that are like super speedy?
Oh yeah, definitely. There's constant time, which is O1. That means no matter how big the problem gets, it always takes the same amount of time. Then there's logarithmic time, O log n, which is really efficient. The time increases way slower as the input grows.
Wow, it's like a whole hierarchy of efficiency. This is making me rethink all the code I write.
It's about working smarter, not harder.
Exactly. But hey, you mentioned something earlier about space complexity. What's that all about?
That's about how much memory an algorithm needs. Think of it like when your desk gets cluttered. You might have the fastest brain, but if you can't find anything in that mess, you're slowed down.
Oh, that's a great analogy. So even if an algorithm is super fast, if it's a memory hog, it might not be the best choice.
Exactly. The book uses the idea of a CPU, the brain of a computer, having limited registers, which is like its immediate workspace.
Yeah.
Even with a powerful CPU, if it can't hold all the data it needs, it'll be constantly swapping stuff in and out, creating a bottleneck.
So we've got time complexity and space complexity. It's like a two-pronged approach to seeing how efficient something is.
Precisely. You need to consider both when you're choosing the right algorithm for a job.
This is amazing. I feel like I'm starting to see my code and even just everyday tasks in a whole new light. This deep dive is off to a great start.
Definitely. There's a lot more to explore in this book.
You know, what's really cool is that this book doesn't just tell you about algorithms, it actually shows you how to build them. And that starts with data structures.
Right. You can think of them like the building blocks for creating algorithms. Like they're the materials you have to work with.
Exactly. And Cheng-Ji does a fantastic job of making them come to life. Remember those analogies he used? Like the parking lot and the train?
Oh, yeah, those were great.
Yeah.
Comparing arrays to a parking lot where each space is like an element in the array,
Yeah.
that really clicked for me.
It's such a clear way to visualize it. You can instantly see how arrays are ordered sequentially, and each element has its own spot.
And the train analogy for linked lists is brilliant. Each train car is like a node. In the list they're connected, but you can also decouple them and rearrange them.
It perfectly captures the flexibility of linked lists compared to arrays.
It's interesting to think about the trade-offs between the two. Arrays are super efficient for accessing specific elements directly.
Because you know exactly where everything is.
Exactly. But linked lists are way more flexible when it comes to inserting or deleting elements because you don't have to shift everything around.
It's like choosing between a well-organized filing cabinet and a stack of sticky notes.
I like that. The filing cabinet, that's your array. Great for quick retrieval, but adding or removing something takes a bit more effort.
Yeah. And the sticky notes, those are your linked lists. Super easy to rearrange and add new thoughts, but finding a specific one might take a while.
Perfect. And the book covers so many other types of data structures, each with its own unique characteristics and use cases. Like stacks.
Which are like what? A stack of plates?
Exactly. You can only add or remove things from the top. It's a last in, first out approach.
Ah, that makes sense. And then there are queues, which are more like a line at the grocery store.
You got it. First in, first out. It's amazing how these everyday examples make it so much easier to understand.
Right. And he doesn't just stop there. Cheng-Ji goes on to explore how these data structures are used in real-world situations, which is super cool.
Oh yeah, this is where it gets really exciting. Think about operating systems. They often use tree structures to organize files and directories.
It's like a family tree for your computer. The main directory is the root, and then all the subfolders branch out, eventually leading to the individual files.
Exactly. That hierarchical structure is super efficient for managing and locating files, especially when you have thousands of them.
And what about databases? I know they rely heavily on data structures too.
Absolutely. They use specialized structures like B-trees and hash tables to store and retrieve massive amounts of data. These are optimized for handling huge data sets and enabling lightning-fast searches.
It's like if you're searching for a specific product on an e-commerce site that has millions of items, you don't want to be waiting forever for the results.
Exactly. B-trees and hash tables make that search almost instantaneous.
That's incredible. And it's not just operating systems and databases. The book also talks about social networks using data structures to represent connections between people.
That's where graphs come in. Each person is a node in the graph, and the connections between them are the edges.
Wow, like a map of the digital world.
Exactly. Graphs are incredibly versatile. They can be used to model all sorts of relationships and networks, from transportation systems to the flow of information online.
It's amazing how these foundational concepts have such a broad reach.
It really highlights why it's so important to understand them. And speaking of understanding, this book doesn't just stay theoretical. It actually dives into the code.
Oh yeah, he uses C to show how to implement all of these data structures.
And that's a smart choice, I think. While C might not be the trendiest language these days, it really forces you to understand how things work at a low level, especially in memory.
You're not just abstractly creating data structures, you're actually allocating memory, working with pointers, seeing how it all gets laid out.
Exactly. It's like taking a peek behind the curtain and seeing the machinery that makes it all work. And the code examples are well written and easy to follow.
Even for someone who's not super familiar with C.
Yeah, definitely. And what I appreciate is that he doesn't just stop at writing the code. He also talks about the importance of testing and debugging, which is crucial.
Totally. It's not enough to just write code. You got to make sure it actually works.
Right. It's all about making your code robust and reliable. And he provides some great tips and strategies for approaching testing and debugging effectively. That's essential for any programmer.
Before we move on, there's one more thing I wanted to highlight. Throughout the book, Cheng-Ji emphasizes the importance of understanding the trade-offs involved in choosing different data structures and algorithms.
Yeah, that's a key point. There's no such thing as a one-size-fits-all solution. Each data structure and algorithm has its strengths and weaknesses.
Like we talked about before, arrays are awesome for direct access, but not as good for insertions and deletions. Linked lists are the opposite.
Right. It's like choosing between a sports car and an SUV.
Ooh, I like this analogy.
The sports car is sleek, fast, but not very practical for hauling a lot of stuff. The SUV is more spacious and versatile, but might not be as agile or fuel efficient.
It's all about choosing the right tool for the job.
Exactly. And this book really helps you understand those nuances and trade-offs so you can make informed decisions. It's about becoming a strategic thinker, not just a code monkey.
Totally. This deep dive has been so enlightening. I feel like I have a much deeper understanding of data structures and algorithms, not just the concepts themselves, but how they fit into the larger world of computer science and problem solving in general. But I'm also curious to hear your final thoughts. What stood out to you? So we've covered so much ground in this deep dive, from basic definitions to real-world applications, even those super helpful analogies that Cheng-Ji uses. But what were your biggest takeaways? What really resonated with you?
What I found most fascinating was how Cheng-Ji makes these complex ideas so relatable. It's like you're having a conversation with a friend, not struggling through some dense technical manual.
I totally agree. It's like he's sitting right there with you explaining everything. And those analogies, like the one with young Gauss and the numbers from 1 to 100, they really stick with you.
Absolutely. It shows why efficiency matters, not just in theory, but in how you approach any problem. And those graphs in the book, they make it crystal clear. The difference between an efficient algorithm and an inefficient one can be huge, especially when you're dealing with tons of data.
It's amazing to see it visualized like that. It makes you realize why choosing the right algorithm is so important.
Exactly. And that's where big O notation comes in. It's like a quick way to see how an algorithm will perform as things scale up.
So like if you're comparing two algorithms, you can look at their big O notation and get a sense of which one is going to be better for a particular task.
Exactly. And Cheng-Ji does a fantastic job of breaking it down, explaining what it means for an algorithm to have constant time, O1, meaning no matter how big the input gets, it takes the same amount of time. And then there's logarithmic time, O log n, which is incredibly efficient because the time it takes increases so much slower as the input grows.
Right. And then, of course, you've got linear time, ON, where the time increases proportionally to the input. And those less efficient ones like ON2, where things can get out of hand really quickly.
It's a whole spectrum. And the cool thing is he brings it back to everyday stuff. Like that analogy with searching for a contact in your phone, that helped me understand how much of a difference the algorithm makes, even for simple tasks.
It's amazing how these concepts are all around us. And it's not just time complexity either. The book covers space complexity too. That's how much memory an algorithm uses.
That's often overlooked, but it's so important, especially when you're dealing with huge data sets.
Right. You could have the fastest algorithm in the world, but if it gobbles up all your memory, it's not going to be very useful.
And Cheng-Ji explains this with that analogy of the CPU and its registers. It's a great way to visualize how memory constraints can impact performance, even if you have a super fast algorithm.
It's like trying to work on a complex project, but you only have a tiny desk.
Exactly. You need space to think, to spread out your ideas. It's same with algorithms. They need memory to work efficiently.
This deep dive has honestly changed the way I think about programming. It's not just about writing code, it's about understanding these deeper concepts and how they impact everything.
Absolutely. It's about becoming a better problem solver, thinking critically about how to approach challenges, and finding the most elegant and efficient solutions. And that's something that can benefit you in all aspects of life, not just in coding.
So well said. Before we wrap up this fantastic deep dive, is there one final thought you want to leave our listeners with?
I would say, remember that learning about these concepts doesn't have to be intimidating. It can be fun. Cheng-Ji's book really shows that. So approach this topic with curiosity, don't be afraid to experiment, and most importantly, enjoy the journey.
That's a perfect note to end on. Thanks so much for joining me on this deep dive. It's been a truly enriching experience, and I'm sure our listeners are feeling inspired to explore the world of data structures and algorithms.
It's been my pleasure, and to everyone listening, keep exploring, keep learning, and most importantly, keep having fun with it.
Absolutely. And that wraps up another episode of The Deep Dive. We hope you enjoyed this journey into the world of data structures. Until next time, happy coding!